Ladies and gentlemen, it's my great pleasure to be here, for the opening ceremony for the 19th International Conference on Electrical Engineering, Electronics, Computer, Telecommunication, and Information Technologies, ECTICON 2022. They say here, hell in Hua Hin. I believe I'm going to change. We are live here in Hua Hin, from I believe it's a convention hall, at Hilton Hotel. And I would like to first of all congratulate all the ECTICON 2022 organizing committees for their effort and successful conference with both people attending from academics, section and industry participant, for many countries. And the conference is aimed to promoting exchange of research output, and also we expect some further cooperation among universities, research center, and industry in the area of electrical engineering, electronics, computers, telecommunication, information technology, signal processing, and other cutting-edge technology. Or you might say you can integrate all of this all together. Besides the regular session this year, this conference have offer various special research tracks, including the special session in agri-tech, where the cutting-edge knowledge in digital technologies help address the modern problem in the agriculture. เกษตรศาสตร์ University, actually the name เกษตรศาสตร์ it is in Thai, but translated in English it's called agriculture science. Maybe agriculture, art and science. Whatever you do, anything that related to เกษตร agriculture. And we hope that the digital technology will help addressing the modern problem in agriculture. And our university understood the importance of the emerging technology. In enabling sustainable farming practice and improving the well-being of our people in the agriculture sector. As a result, we hope that this special session will generate excitement in the research cooperation, especially in the field of agro technology. And finally, at this moment, I would like to officially start ECTICON 2022 conference. Thank you all for participating and hope you enjoy your stay online and offline, wherever you are. Thank you very much.
Thank you very much, sir. Next, may I invite Professor Dr. Wittiphong Arikun, President of the ECTI Association, for the welcoming speech. Thank you.
Okay. Good morning, ladies and gentlemen. On behalf of ECTI Association, I would like to thank you all for being here to support our ECICON 2022. This is the 19th consecutive conference and the flagship of the conference of ECTI Association. First of all, I would like to thank Professor Pirayut Chansetikun, Dean of Faculty of Engineering, เกษตรศาสตร์ University, Thailand, for giving priority to support our activity. He is now here only to help us, and he will return to his busy work in this afternoon. We thank you for your precious time. Next, I would like to thank our three general co-chair, Professor Sinchai Kamonpiwong, Professor Nitipat Tirkarawanish, Professor Thirasit Kaset Kasem, our technical program co-chair, and our organizing committee. I know you dedicate your time and effort to make this conference happen. I'm so grateful for all of your help. As you know, the ECTI Association is a non-profit organization. Hence, we are doing this to support the research activity in electrical engineering, electronics, computer, telecommunication, and information technology in Thailand and in the region and around the world. I will be here all day. If you have an idea for improving our or leading the ECTI Association into the future, please come and talk to me. I'm very welcome all of you in any comment. I'm all ear. And I would like to hear comment from you. Again, thank you very much for being here online and on site. Welcome you all to ECICON 2022. Thank you very much.
Thank you very much, Professor Dr. Wuttipong Arikun. Next, I would like to invite Associate Professor Dr. Nitipat Thirakawanit, General Co-Chair of the conference, for the welcoming speech, please. Thank you.
Good morning, ladies and gentlemen. The President of ECTI Association, Professor Wuttipong Arikun, the Dean of Engineering Faculty, Kaset Sat University, Associate Professor Priyut Chan Setikun. First of all, good morning to every participant who are in this room and who are online from all over around the world. Okay, welcome to ECTI conference, ECITCON 2022. Okay. First, may I thank every member of the conference committee and the staff for helping in organizing this event. And I also want to thank our participants who are spending their effort to travel to Thailand to join this event. All right. This year is quite special because it is the first time that the conference is being hosted on site after 2 years of COVID-19 restriction. So this is quite remarkable that we can have an opportunity to discuss in person in a physical room rather than online room as in the past 2 years. I'm glad that this year I can speak to all of you in a much more positive context, with real physical discussion. I also want to express my gratitude once again to every speaker that present their papers in this conference. The quality of the presentation is quite remarkable in this year. Okay. And lastly, as you can see, Hua Hin is a very beautiful place, a perfect setting for the conference. So I hope that everyone will enjoy the conference. So it is now my great pleasure to officially welcome everyone to the ECTICON 2022. Have a good time together. Thank you very much.
Thank you, sir. The next thing we will do is that we will take a group photo. So may I invite the conference committees, technical program chairs, okay, to take group photo together on the stage, maybe. Thank you very much. คือ next photo ไหมก็คืออันนี้ committee ก่อนแล้ว next photo maybe on the stage please Professor Sinchai please anyone Professor Suttipat Professor Phulap Professor Achara You know who you are. You can come out. The next one will be for everyone. Okay. The first photo will be for committee and technical program chair first. Yes. Can I invite everyone to take a photo together? Everyone in the room, participants. Yes. Bye. Also the staff. You can take photo together. Also the staff. Everyone and also the staff also. You can come here with the green shirt, the green t-shirt. Okay, the online presentation. Could you show the camera? I mean, turn on the camera so we can see your face. We can get good photo of also online participants. Thank you very much. Open the camera, please. Turn on. Everyone, please. We have. Oh, this is very good. Hybrid. Okay, real hybrid. We are waiting for you. Please turn on the camera. Everyone, thank you. Okay, thank you very much. Also, online participants and everyone. Next, we will have keynote speakers. So we will arrange the table a little bit. Sorry. It's going to be online speaker, right? Okay. So so we will have 3 keynote speakers today. They are all online. Okay. So may I give the floor to Assistant Professor Dr. Suchai Bunto, Chair of the first keynote speaker, please.
Thank you very much. Okay, it is my honor to introduce the first keynote speaker, President Hiroshi Arai from Society of Instrumentation and Control Engineer. President Hiroshi Arai received his Master Engineering degrees in Electrical Engineering from Waseda University in 1981. He joined Yamatake Honeywell or Asbuild Corporation in 1981. Since then, he developed a distributed control system or DCS. He also took a lead of introducing ERP package as managing executive officer of Asbuild Group Information System and IT Software Technology. Now he is the president of SAIS and interested in collaboration and of academia and industry. The topic that President Hiroshi Arai will give talk today is the law of measurement and control to solve social issues and potential of academic societies to shorten the distance between academia and industry. So, President Hiroshi, you can start the talk now.
Okay, thank you very much for introducing me. I'll show you the slide. So please give me a time. Can you show my slide? Is it okay?
Yes, I can see your slide.
Okay. Okay, now I will start. Let me start. Again, thank you very much for attending my keynote session. And thank you very much for ECTICON members and professors and staff to give me such a great chance to present about science and the industry. My name is Hiroshi Arai, and as I introduced, right now I'm a president of SAIS, and also I'm working for as an advisor regarding to IT and DX. So let me start. The Today's title is Role of Measurement Control to Solve Social Issues and Potential of Academic Society to Shorten the Distance Between Academy and Industry. Here is today's content. First of all, I'd like to introduce myself. Already I introduced, so it will be short. And also I will introduce overall size. Then I will explain role transition and changes of size. And also then I will explain industry's trend by using my company's example. I will show you one video and I will present some new services. And then I will confirm size mission and the new size policy. And then finally, I will explain real examples of activities based on the new size policy. I will call it Size Industry Initiative. And these are cooperation with Jemima regarding about safety and smart security area. And also, I will explain activities of international conferences sponsored by SAIS regarding the industrial activities. Already, Professor I introduced me, so I do not repeat this, but now I have a chance be a president of SAIS, and I'm interested, as he said, in a collaboration with academia and industry. In this video, I will explain the overall of SAIS. SAIS stands for Society of Instruments and Control Engineers, as you know. It was established 1961 September. Chairperson, president is me, Hiroshi Arai. Currently, SAIS has about 4,700 members and 175 corporate members. SAIS has 6 technical divisions: measurement, control, system and information, system integration, industrial applications, and life engineering. And we have, SAIS has also 6 local chapters from Hokkaido to Kyushu. Hokkaido is the northern part of Japan. Kyushu is the southern part of Japan. SAIS has local chapters in between them, including these 2. SAIS realizes innovations that contribute further industry, future industry and society by measurement, control, system engineering as a hub for promoting open innovation. In this view, I will explain the transition of academic society and its role, and the issues of the academic society from current industry point of view. As shown here, from 70s to 90s were an era of growth through industry academia cooperation. At that period, expectations from industries to academies are the establishment of basic theory for stable operation of petrochemical, steel, and electric power plants. At that time, SAIS has steady increase in number of members and also increase in attendance at academic seminars. And then research subjects have moved to IT systems and network systems. At that time period, expectations from industries are expansion of target fields to factory automation, and optimization of management and operation efficiency. Strengthening alliance with overseas partner due to business globalization. At that time, SAIS activities are SAIS established 6 department organization due to the expansion of target field. And also, SAIS internationalized itself. Annual conference is internationalized, and SAIS had published in English magazine. I think it's stable days. These are the stable period. However, about 2020, However, since the mid-90s, the expectations from industry have gradually decreased, and the activities and appeals of academic society have gradually decreased too. So I think the activities of academic society have to be changed. Furthermore, after 2020 around, due to the rise of the new technology such as AI, IoT revolution, and Society 5.0, etc., and changes in social needs, the expectation of industry become open innovation and securing human resources. Under the such circumstance, I think the gap is highlighted by the situation in which lacking the size digitalizing its effort to tackle social issues, lacking appeal its activities, and according to that, expectations from industry are declining. As a result, the number of corporate members and the number of regular members has decreased. As I described, for a long time in instrument and control area in Japan, academia and industry dive their role such that academia society establishes the theory and the industry companies and the societies applying them to the society. But with the passage of the time, the role of academic societies required by industries is changing from the division of role between industry and academia to the era of collaboration. Okay. Now I will show you my company's as-built video as an example of control industry company's new direction. This video shows my company's trends and direction, but all other control companies are targeting same direction. So please watch the video. It will take 3 minutes. Let me. Can you see the video? Yeah. Okay.
I cannot see your video.
No? You cannot see the video yet. You cannot. Okay.
Maybe the video is in the other window.
Okay. Let me do this.
Professor, we are going
Yeah.
to play the video that you sent us
Yeah. Okay. But I will.
2 seconds.
Yeah, I will do that.
Today, our society faces a time of great change.
Okay, I can see the video now.
You can see you can hear the voice also?
Yes, I can hear the voice.
Okay.
The evolution of IoT and AI amidst the emergence of the 5G era is creating trends in technical innovation. Furthermore, the spread of COVID-19 is accelerating changes in society, corporate business environment, and work style. As such, the required role of automation is becoming increasingly important. There is a demand for swift measures to meet social transitions in areas such as production sites, households, office buildings, and facilities. At the same time, corresponding to changes in work style, protecting workers' health, and promoting digital transformation have also become significant.
Professor, did you see, are you looking at the
Group strives to
video?
I can see only the picture.
Oh,
Video doesn't move.
okay. Hold on. Sorry.
Hello. We can play the video here. If you don't-
Okay. Yes, please. Then I will cancel the sharing the video. Please show the video, please.
Yeah, we are arranging that in a minute.
Okay.
Today, our society faces a
Thank
time
you.
of great change. Globalization, declining birth rates, and an aging population are causing society to undergo structural changes. The evolution of IoT and AI amidst the emergence of the 5G era is creating trends in technical innovation. Furthermore, the spread of COVID-19 is accelerating changes in society, corporate business environment, and work style. As such, the required role of automation is becoming increasingly important. There is a demand for swift measures to meet social transitions in areas such as production sites, households, office buildings, and facilities. At the same time, corresponding to changes in work style, protecting workers' health, and promoting digital transformation have also become significant issues. The as-built group strives to combine its long-cultivated measurement and control technologies and knowledge with cutting-edge innovations like IoT, cloud computing, AI, and big data to resolve social and industrial issues, as well as provide state-of-the-art products and services. The as-built group will pursue new automation by strengthening the development of devices and field equipment, along with applications and cloud-based services that support them. In this new age, the as-built group utilizes advanced technologies to meet the needs of the evolving industrial society. The as-built group's new automation will connect more closely with customer sites and enable us to build the society and industry of tomorrow together with customers. Since the as-built group's founding, our business activities have contributed to resolving various social issues. We are aware that our business is directly linked, in series, to the shared goal of realizing such a society. As the role of automation expands, the as-built group is undertaking specific measures to achieve the United Nations Sustainable Development Goals. In cooperation with customers, all business activities and employee efforts are dedicated to resolving social issues. The as-built group contributes in series to the achievement of a sustainable society through human-centered automation.
Okay. Thank you very much. Show my video.
Give us some time to send you back to a presenter.
Okay. Right now I can't share my content, so could you give me? Oh, okay.
I think you
I
can
will-
share now.
Yeah, I can do that. Now, everyone can see my video, my slide.
Yes, I can see your
Okay.
slide.
Thank you very much. So thank you very much for watching our video. As I said, it is my company's video, but it is just an example. All companies, industries are targeting same direction. And in addition to the previous video, I will add as-built academic activities in Thailand and in this area. As-built has a factory and sales subsidiary and control valve center in Thailand. So various kind of we have equipment. And this center has many programs. This valve center has control valve maintenance center has many programs, such as maintenance program, analysis for failure records, remote maintenance, modification to meet new regulations and standards, 24-hour emergency service, precise inspection of the control valve with bench test machine. And also we have on-site support service, public inspection and verification, equipment diagnosis, collaboration checks. And then right now, Asbil has announced the new service, which called the DX Valve Cloud Service. This service changes the maintenance scheme from time-based maintenance to condition-based maintenance, TBM to CBM. Furthermore, it will increase efficiency of CBM and maintenance quality. As shown here, the positioner attached on the control valve has become smarter one, and the data is continuously collected and sent through the PC in the field to the cloud. The control valve data of entire plant is collected and monitored on the cloud, and these big data was analyzed by using AI and algorithm on the cloud computing power to visualize the situation in real time. Maintenance people can check valve's condition currently running at any time from anywhere, and also cloud service sending alarm to the maintenance people when serious condition is detected. As a matter of fact, half of the valve do not need maintenance, just cleaning. That's why the changing from TBM to CBM is very efficient. And also, unexpected shutdown of control valves is decreased, because valve condition is continuously monitored and checked by the cloud. These are the trend and the direction of control companies. In other words, the industry automation companies and association is trying to solve social issues by implementing new automation technology like AI, IoT. Other words, they are trying to contribute directly to the SDGs. Returning to the SAIS mission again, the mission statement defined it as follows: as the core academic society for measurement control systems, pursue the knowledge across the various fields, create a new value, contribute to the extraction and resolution of social issues by becoming a hub for related fields, industry, academia, and government, and through disseminating and the collaborating. Until now, SARS has been conducting many research activities that can contribute to solving the social issues based on the basic technology of measurement control and systems. They are directly connected to the SDGs. For example, with SDGs Goal 9, Industry, Innovation, and Infrastructure, I'd like to disseminating the research result of CPS, which is exactly strength of SAIS, which is a fusion of measurement and control and systems. In addition, number 13, climate action is a research area that SAIS specializes, such as advanced measurement, remote sensing, and multi-scale global simulation. Regarding to Global 7 affordable and clean energy, we have been conducting a lot of researches that contribute to carbon neutrality, such as optimization and control of energy supply and demand systems. By expanding these activities to areas of activities that are conscious of the SDGs, strengthening appealing them, I think science and academia can further contribute to solving social issues. Now I will set new science policy. Celebrating 60th anniversary of last year, we will return to the mission as a new science industry initiative. We lead the science to the hub of industry, academia, and government. Our outreach to non-science members to promote cross-cutting field activities. We would like to contribute to the solution of social issues by sustainable society management. I will carry out activities under the science industry initiative. The purpose is to expand science's contribution to solving social issues driven by shortening the gap between academic societies and industry companies. By doing so, we aim to be one of the cornerstones of science activities to provide a place for research activities, information sharing, and the correlation of human resources to solve social issues based on the foundation of measurement control strategy. As a concrete plan is retaining and expanding supporting members, corporate tour, corporate recruitment, placement, single donation window, industry association, academic society cooperation with JEMIMA, ISI, JASE, IFAC, and IROS. JEMIMA stands for Electric Japan Measurement Instrument Manufacturers Association. JSAE stands for Society of Automotive Engineers of Japan. ISI is another academic society of control engineering in Japan, and you know very well about IFAC and IROS, I think. Enlightenment of standardization activities, International Standardization Award, annual conference organization sessions, especially industry area. These activities are not only limited to the science members, but outside of science members. The goal is to work together with industry and academia to tackle social issues through these activities. I will explain specific activities for examples. First one is cooperation with JEMIMA, and the next one will be international conferences. This view shows the cooperation with JEMIMA, Safety Task Force and Smart Security Area. In size, working group about measurement and control and system for safety was established a little bit long time ago. In order to prevent large-scale accident, it is necessary to combine an inductive approach based on the lessons of industrial accident and disasters, a deductive approach based on the theory of academia, and emergent approach based on the hypothesis testing. This working group are discussing the currently safety engineering and technology, including cybersecurity and next generation instrument and control system. And also, this working group discussing how to realize a sustainable society by using new technology such as IoT, AI, and CPS. And then at JEMIMA, Smart Security Review Working Group was established in 2020. So, these two working groups are planning to work together right now. Seminars and studies sessions regarding this area in collaboration with SAIS and JEMIMA is planned. and study sessions with working group also planned. Through these activities, I'd like to shorten the distance between engineers and researchers in the industry and academic societies and digitalize them. I would explore such activity with other industry groups. This view shows international science conference sponsored by SAIS. Many industrial academia collaboration activities are planned at these international conferences. At annual conference 2022 in Kumamoto, we're planning collaboration between industry and academic societies under the name of industry track. The World Congress of International Automation Control Union, IFAC, will be held in Japan in 2023. But prior to the event, more than 120 industry academia members from various industry fields have gathered such an industry group and actively planning right now. Through collaboration and support with this industry group, SAIS aims to reach out to new industry fields. There isn't in this view, but IIFS Osaka in 2022, conducted by Jemima and sponsored by SAIS, in this exhibition are lectured by a SAIS professor and a collaborative panel session by Jemima, NECA, and SAIS are planned. NECA stands for Nippon means Japan, Electric Control Equipment Association. That's all my session today. Thank you for your attention. I will continue to promote activities to shorten the distance between the SAIS and the industries and other SAIS industry initiatives. Thank you very much for attention again. That's all.
Thank you very much, President Hiroshi, for the very nice talk. Since the time is quite limited, I think we can have only one question from the floor and also online. Do you have any question? Okay, we have question from Professor David Manjatpongchai from the chat. The question is, how does SAIS promote the control engineering to young generation students?
Oh, okay. We have a lot of class for students, not only for not only for the university student, but also for the high school student. And also we have a special education program for young girls. So we train them what is a PID, what are the control theory, so on. These teachers are coming from universities and industries, both. That is my answer. Okay.
Thank you, President Hiroshi. I think the time is quite limited, so we cannot give more any question. But if you have on the floor and also online have any more questions, you can. I think you can send email to President Hiroshi directly.
Yes, please.
Okay. So at the end, I would like to thank again President Hiroshi for the very nice speak. And I would like everyone in online and also on the floor give thank you to President Hiroshi as well.
Thank you very much.
Thank you. Okay, I should give the floor to the other session chair.
Thank you, Professor Alai. Okay, so we have another keynote speaker. Let me get my go ready so that I get everything right. So, ladies and gentlemen, good morning. Today we have a great pleasure to have our second keynote speaker, Professor Kiyoshi Honda. Professor Honda obtained Bachelor of Science in Agriculture in 1982 and Doctor of Engineering in 1992 from University of Tokyo. He served Nippon Koei Mie University, Asian Institute of Technology. Currently, he is a professor at Chubu University, Japan, and Chief Strategy Officer of Listenfield Incorporated. He has more than 30 years of experience in remote sensing research. His recent focus is the development of an interoperable analytical platform for agriculture. Today's talk is in the title of Analytical Data Platform for Smart Agriculture. So, Professor Honda, if you are ready, please start your presentation.
Thank you very much, Mr. Chairman. Can you see my screen?
Yes, I can.
Yes, Professor. Okay. So today I'd like to present analytical data platform for smart agriculture. So this is the content is the achievement of our research, my research, and as well as the activity of Listenfield company. As introduced by the chairman, I have worked for Asian Institute of Technology for 15 years. So I'm very happy and honored back in Thailand, even virtually. I was a full-time faculty of Asian Institute of Technology for 15 years. So I feel that Thailand is my second home country. And we have been working on the research. Actually, I am from agriculture university. I graduated from agriculture college of University of Tokyo, and then I worked for remote sensing, and then we worked on IT agriculture for quite some time, and then we thought that we have to really apply what we have developed in actual agriculture site. So that's why we established Listenfield in 2017 with my co-founder, Dr. Rasalan Sinashotiranan. We are facing serious climate change, which has significant influence to, of course, to agriculture. This graph, can you see my pointer? Then this graph shows the temperature change in 120 years in Hokkaido, Japan, north part of Japan, which is the largest grain growing area in Japan. You can find the temperature is rising steadily, especially in case of minimum temperature, it rose 4.75 degrees Celsius in 120 years, or 0.4 degree a year. As you can see here, so this research found that 1 degree increase of minimum temperature reduces 10% of grain yield, which is a significant impact. I have analyzed the temperature change in 30 years in Thailand, and all points show the significant increase of temperature similar to this, similar to the case in Hokkaido. So this kind of change is actually everywhere in the world. The climate change also changed the pattern of rainfall, occurrence of extreme weather, which also changed the best timing of planting, suitable crops and varieties, and increase the risk of agriculture disasters. So we have problems to address under the climate change. So this blue graph shows the demand of cereal crops in the world. The demand has been steadily increasing, as you can see, not only because of population increase, but also by the increase of meat consumption. People start to eat chicken, pork, and the beef, and then the animal demand more food. So even if the population increase is not high as before, but still the demand is growing. Free trade agreement request to improve the efficiency of domestic agriculture, which has been well protected by subsidies. And the aging of farmers is an issue in the world. In Japan, it is a serious issue, and I heard that in Thailand also an issue. We need to respond to these problems by changing farm management, which called as adaptation, to achieve higher productivity while controlling the risk. Agriculture is considered as a significant source of greenhouse gas emission. We need to change conventional farming to environmental friendly farming. However, we do not have experience in the changing climate, then what we need is data-driven agriculture. We need to make decisions based on data. So to make decisions, we need to answer many questions. So such as, do I need to change sowing date to secure yield and limit the risk? So farmer doesn't have experience in the changing climate, so it's difficult to answer to this. I could not sow because of bad weather. Should I still plant or give up and wait for next crop seasons? Rainfall pattern is changing. Actually, in Hokkaido area, before in September when the farmer plant wheat, it didn't rain, but currently it rains in September. If it rains, the heavy machine cannot go into the field, and then farmer cannot plant. Then farmer has to make a decision. Okay, then plant in October or give up. Seasonal forecast is a forecast saying that the next season will be high temperature or low precipitation as a probability. Then how can when farmer can get this kind of seasonal forecast, then how farmers should behave or respond to this kind of forecast is the question. And in Japan, we now the aging society, then many farmers give up to cultivate their field. Then they ask the company to cultivate. While they're requesting, don't touch to the shape of their fields. So companies has to cultivate like hundreds or thousands of rice fields, and then where and which variety and which field and when to plant, so that they can harvest with limited harvester resources. And companies, agro companies, they usually have many contract farmers. From farmers, they are buying the raw materials. Of course, so company want to operate the factory 100% efficiency, but they don't want to have the excess products because they have to buy the products from farmers. Then how to guide farmers? They want to direct farmers that, okay, then please plant this variety, this timing, so that they can have a stable, continuous, and then just enough material supply to the factory. So how to answer to these questions? We need to simulate. Then we have to observe, calibrate, model, simulate, and optimize. That is the answer. So then we are proposing scheme shown here that fully utilize geoinformatics and ICT for modeling and simulation. We have a lot of Earth observation satellites, and recently Space Agency or companies have launched the so-called constellation satellites, which provide us with a very good resolution in terms of space, I mean the spatial resolution, and also time resolution. So which actually changed drastically the application of satellite images to agriculture. Drone or UAV is now very popular, as you know. And thanks to the extension of mobile network extension, then we can deploy the field sensor network rather easily than before. Then But these kind of information, satellite, drone, field sensor networks, so those are actually the snapshot of the field. Then you can know that it's not easy to use this data directly to answer to the questions raised in the previous slides. So what we propose is we use this kind of information into the model calibration. There are several crop models in this world, thanks to the effort of researchers. So we calibrate these models. And then once we calibrate the model, then we can do a lot of scenario simulations. So this graph shows the one example. X-axis is the irrigation amount, and the Y-axis is the yield. So currently, they are giving 300 millimeter of irrigation. We simulate that if they optimize irrigation schedule, so they can increase the yield from this point to this point. And if they give more 100 millimeter, they can increase to in this case, around 5,400 kilogram per hectare. If more than 500 millimeter, then it doesn't increase the yield. So it shows that when they can plan the irrigation facilities of the capacity up to 500 millimeter. So this kind of scheme can convert this kind of observation data to higher level of actionable information. So we want to provide this information at real time to farmers and agro businesses. So how the model looks like. There are several crops model available, like DSAT, AppSim, or Simulus. So these are the popular model. These models try to simulate the response of the crops to the environment. Environment is given by users, by like a temperature or rainfall or solar radiation, and then it simulates the soil moisture, and then simulate the response of the plant, which is a chemical response and the physical response. And then it can output when it flowers, when maturity happens, and then how much of a grain or yield can be achieved. But as you can see, the model is complicated and the calibration is not the easy work. Even if we have a good model parameters, there is a big uncertainty, which is weather. There is no technology now to predict definite weather for several months, which is a crop growing period. Then how to deal with this big uncertainty? Even if we have a good model, if we don't have a weather scenarios, we can't simulate. Our answer is to generate a possible weather scenario in a stochastic process. Then we predict phenology and yield as a distribution which shows stability and risks. At the time of planting, the uncertainty is the highest. When the time passes, we can get a real observation, and then we update with the scenario by this observation and then reduce the uncertainty. We can reduce the degree of uncertainty using seasonal forecast. Seasonal forecast is a probabilistic forecast. It forecasts the probability of below normal, this region, near normal, and above normal. Without simulation, so they are all 33.3%. But by running global or regional GCM, General Circulation Model, so National Meteorological Department or Research Institute issues the forecast. For example, this is the with a seasonal forecast from IRI of Columbia University. So now this is the issue of May 2022, the most recent forecast, and it shows the probability of precipitation rainfall, and then it says that in Indonesia the precipitation will be high with a probability of more than like 70%. So this is most likely scenario that precipitation in Indonesia is highest. While while there is some probability that rainfall is in near normal or below normal. So how can we reflect this kind of seasonal forecast into simulation? So we generate a scenario that fits to the seasonal forecast. This is one example of a temperature scenario. So usually we generated 200 or 400 scenarios, and then all scenarios are different each other. So we use that kind of scenario and then simulate. For example, this is the this is a simulation of wheat growth in Hokkaido. So this is a winter wheat. So they plant before the winter, and then when it snows, the wheat sleeps under snow. We call it binary,zation, and then next year it goes up. It starts to grow up again. So if they plant in August, the yield suffers a lot. And then at the beginning of September, like the first week of September, the yield is the highest, while you can see there are significant risk of low yield. And then come to the mid of September, the yield reduced a little bit, but the risk has also reduced significantly. So usually farmers are planting this kind of timing. But now in Hokkaido, so sometimes it rains in September and they cannot plant. So they have to plant. If they plant, they have to plant in October. So you can see some reduction of yield. So farmers can decide if they can accept this kind of reduction or not. And then they can make a decision, plant or not plant. So this kind of simulation can give the actionable information for farmers. So general base workflow of this kind of process is expressed in this way. So we use a historical weather data which defines the climate. Climate can be defined by the 30 years of the weather observation. We characterize the climate, and then we use a weather generator, and we put the long-term seasonal forecast, and we generate weather scenarios. Weather scenarios can be updated daily base if we have the weather station nearby, or we can interpolate from the stations around the target point. And then we feed the data into crop model. We put the crop management scenarios such as when to plant, which crop, which variety, and how much of fertilizer, how much water to give, and then we can simulate. And then we show the result in the good graphical user interface to farmers. So actually, it is not too difficult for researchers to perform this kind of analysis by writing a program and then run the program on their PC. But we want to provide this kind of calculation to farmers. So we need a scalability. So what we have been doing is developing the API platform on which the software developer can do the same as a researcher can do. So we connect the weather database through agro-environmental data APIs. Then a client can call just this API, and then without knowing how the weather has been observed, so they can get the data. And then they can feed the result into weather generator API, and then together with soil profile API, then they can put the result, they can flow the result into crop model APIs. And then the result of crop model API can be shown to users on the applications. So this is the like a rough sketch of our API platform, which makes it possible to analyze the data on the cloud. So, but when we perform this kind of data flow, when we construct this kind of data pipeline, the interoperability is the issue. For example, the we deal with many types of weather stations, and then how they implement physically in the site is very different from system to system. So if we have to write a program adjusting to each system, it is too much to develop the applications. So we deployed the standard web API for geospatial data. OGC, Open Geospatial Consortium, is the standardization organization for geospatial data. And then one of the standards they propose is Sense Observation Service, which provides interoperability to environmental data. There are three queries, such as get capability, describe sensors, and get observations. Then user can issue this query, and then they can get the metadata and data without knowing the physical setup. So we have been connecting these kind of sensors. And then if we have to write the program one by one, it is too much. So we put the OGC's API here, Sense Observation Service. So we issue the get capabilities, and then client application can get a list of the SOS stations and what kind of properties are being observed. And then issue the get observation, and then they can get the sensor data with timestamp in the ISO format. Then simulation system or GUI application doesn't need to know the complexity of physical setup. We have been proposing this kind of naming convention, even though the SOS defines that when SOS get capabilities, server has to respond the locations or observed properties. But if we don't have a standard of observed properties, it's difficult for application to understand what they are observing actually. For example, air temperature. So sometimes the system say temp, sometimes system say a temp or T, or in Japanese, kion or ondo or something like that. So even if a server is telling that I am developing the temp, so client cannot know is this really air temperature or soil temperature. So we propose this kind of name convention. And then now this kind of name convention is published by the cabinet of Japanese government, and then being recommended to IT agriculture software developers. So which increase the interoperability of the data. We have been working in Thailand. We have been working with Thai farmers and the Thai agribusinesses closely. So weather data in Thailand is quite important for us. So we are getting the Thai meteorological department data every day, and then we are providing sense observation service. So we can cover, I think, as I remember, around 120 weather stations are being served by our sense observation service platform. The density of the weather station in Thailand is around 50 kilometers, which is actually not enough. So we also implement the interpolation APIs with integration with NASA Power, which provide the global data service by NASA. And also we integrate with our own weather stations. So client can access to this weather data without knowing from where actually they are getting the data. In Japan, NARO, National Agriculture Research Organization, developed 1 kilometer grid weather database, and then they are now serving as a commercial services. They are serving NetCDF, which is a little bit difficult for usual software developer. So we developed the sense observation service wrapper for 1 kilometer grid, so that client can access to the data without effort. Soil parameter is very important that govern the soil moisture conditions. There are several soil databases in Japan or in the world, but their format is different from different each other. So we make the API service, which provides the soil profile information that fit to like a DSAT simulation software. Actually, agriculture community is proposing the ICASA format, which is a standard for agriculture simulation, crop simulations. ICASA format is not very popular, but we found that even NASA Power, which has been I have introduced here. So if you request, you want to get the weather data by ICASA format, actually you can request. We developed the weather generator API. You can set the data source or location and time range of the scenario, and then you can get the weather scenario. The result is given by metadata and then linked to weather files. The weather file is not too small, not so small. So we want to avoid the back and forth of the data between client and server. So basically our scheme is user request, and then result is returned by URL that is pointing the result. Crop simulation API, this is what we developed. So user can give a location, crop, variety, and weather scenario. And then you can switch the model here. Like in this case, it is saying Simu, or you can change to DSAT, and then you can get the data. You can get the result by URL, and then you can visualize the data at your application. So we published the API document so that the user can use. Currently, we are providing this API to several, two companies, one in Japan and one in Thailand. So they have their own interest how to present their results into their customers. So they are developing their own application on top of our API platform. So this is one example that what kind of application can be developed. So as you can see, this is the before the planting. All of weather scenarios such as precipitation or solar radiation or Tmax or Tmin, they are very different. And then when they plant, so data can be updated here. And then flowering date, maturity date, and the expected yield is shown here. And then as time passes, we update the weather. So all scenarios are becoming same day by day, like this. And then it shows how maturity date prediction was updated at the time of the planting. It predicts with this kind of range, but as time passes, the simulation converges to one date. We also developed a SDK so that the user can write the program rather easily. For university researchers, API call is still a little bit hard work, but writing Python code is not difficult for usual nominal researchers. So we follow the G by E by M concept, which is genotype, which represent the characteristics of crops, environment such as weather, management, this is like a crop or the fertilizer and so on. Then user can define G, genotype is crop is rice, variety is KDM 105, environment is weather, which should have come from the weather generator. Management, planting date is this date, fertilizer day after planting 0. So at the same time of planting, the amount, how much of amount of fertilizer to give, and then just call crop simulation G by E by M. Then they can get the result. So this makes the simple application development very easy. We can develop using that kind of SDKs or API that wraps the SDKs. So this kind of crop simulation application can be developed in very short time. So we could develop this kind of application in 1 or 2 days. Crop model parameters is one of the issues that when we simulate. So we are putting a lot of effort to obtain the crop model parameters. We set up our own weather stations. We set up in sugarcane field or experimental rice fields. Then we observe the growth of crops, and then we calculate the model. And ListenFeed is providing application on top of this, which has been developed on top of this API platform. So our concept is the farmers input the data, and then farmer can get advice from agronomist. Agriculture community or agribusinesses, so they have agronomists, and then they share the information between farmers and companies. Agronomists give a service advices to farmers, and then they can be the relation with win-win relation. So farmers can use this kind of mobile app, and they can input their fields, they can input their management, and then the company agronomist visits the site, looking at the weather, looking at the satellite images, and then they give advice to farmers. The communities or agrobusinesses, they can see the overview. They have several hundreds of contract farmers, and then they can monitor that how the harvesting is going on. And we are trying to produce more higher level of actionable information. For example, when and which variety to plant for many fields so that they can harvest smoothly. Or we can provide this kind of confident range of product supply to the factory. So it shows a 50% range of the confidence range of the products. So they can use this kind of information so that they can operate the factory efficiently. So one example of smart agriculture is a simple case is like this. Farmer input the planting date when they plant. So they said, I planted now. And then we run the simulation, and then it suggests your maturity will happen this date, probably like 60 days or 90 days later. Then our system guides them to the machine reservation site. And then they can select appropriate machines, and then they can immediately reserve. Then farmers can use the harvester at the right time, and then contractors who are the owner of this machine can automate reservation management. So which is a simple but very efficient application of smart agriculture in actual fields. So we have many users. Now, currently, we have 20,000 users in Thailand. Luckily, in Thailand, all farmers have smartphone. They are using Line, and then there is no obstacle for them to start to use our application, which is very nice. So now I would like to conclude my presentation. Analytical API platform for data-driven smart agriculture has been developed, and then it realizes scalability and the local service of the high-level analysis to many farmers. We want to develop more various actionable information for management. And one thing that we would like to work on is quantifying the contribution to environment. We want to quantify the carbon footprint by agriculture. They are using chemical fertilizer. Chemical fertilizer requires a lot of energy when it has been produced. So we want to account how much of greenhouse gas emission has been involved by use of the chemical fertilizer, or even running the agriculture machine. Carbon sequestration is one of the hot topic. there is one big project, 4 mill project. If all agricultural fields start to accumulate carbon every year 0.4%, then it can offset, as I remember, around 10% of total greenhouse gas emission. Then finally, we want to convert that kind of a contribution to carbon credit and then distribute to stakeholders so that they can have a good incentive. We want to promote more the collaboration with research institutes and agribusiness and farmers. They are our customers and investors. Recently, we have accepted the investment from Kubota, and then we are now collaborating closely with Kubota. So that's all, and thank you very much for listening to my presentation. Return to Chairman.
Thank you very much, Mr. Honda. I think we have time for maybe just 1 or 2 questions. So, is there any question, both from on-site and online? So there's some person said, "Can I have your slide?" There's one. Okay, I think then I ask one question. What do you think about what the government role should be in the data platform? So what role of the government should play in this?
I see. Yeah. Okay. One problem we always face is the getting the weather data. Each government run the weather stations, and then this is a very basic and fundamental data for agriculture. So if government can play a role for more open data, that would be very beneficial for this kind of system.
Okay, thank you very much. There's one question from the audience.
You said that for every 1 degree of rise in temperature, the yield is decreasing. So this is the only observation for Japan, or it's globally observed phenomena, sir?
Yeah, I have found one research paper. So that is the show. So they have checked the actually this is not my research, but their research. Rice is declined with higher night temperature from global warming. So they check the data, I guess not in Japan, in several places. And then they found, I think they checked the impact to rice, in this case, Philippines. I thought that yield decreased because of respiration. But they say that in some crops, it cannot be explained by only the respiration, but because of some mechanism. So this paper point out that there must be some more detailed research why and how the yield reduced by the rise of the night temperature.
Okay, thank you, sir.
Thank you very much. I don't think we have any time for more questions though. So if you have any further questions, you can send email to Mr. Honda personally. So let us thank Mr. Honda again for giving us a talk today. Please give a big hand to him.
Thank you very much.
Right. So we have lunch here in this conference. Our staff will escort you to lunch location. Please come back here at 1:15. We have another keynote speaker at 1:15. So don't forget to come back in maybe having your lunch in 59 minutes. All right. Thank you very much. Okay. See you in about 59 minutes.
Okay, thank you.
Okay, I think it's time to start the afternoon session. Well, good afternoon, everybody. Welcome back to the keynote speech of this afternoon. May I introduce myself again? I am Nitpat Thirakamnit from Kasetsart University. For this afternoon keynote, I'm glad to have Professor Alberto Castellazzi with us.
Thank you very much.
Do you hear me?
Yes.
All right. So maybe I will give you some information about our keynote. Professor Alberto Castellazzi is a professor in Kyoto University of Advanced Science in Engineering Department in Japan, where he leads research and teaching in advanced solid-state power processing to yield disruptive joint progress in efficiency, power density, and reliability of power converters. He has published over 200 papers in international journals and conference proceedings, and has held a number of invited talks in the topic of wide bandgap power devices and silicon carbide-based electrical power conversion. Well, he is active as both a reviewer and editor, and a member of the technical program committee of a number of international conferences on power electronics and power semiconductor devices. In addition, he is also my supervisor during my PhD. So I am very excited and very glad to have him today. So the topic of the speech will be topologies and technologies for advanced wide bandgap power conversion. Professor, if you are ready, you may start your presentation.
Thank you very much. So I have now gone in a full presentation mode. I hope you can see it. Okay, thank you very much again for the invitation and for the introduction. I hope next time to be able to visit in person. So to start today's topic, so what I'm dealing with is power electronics, and I wanted to introduce the topic as I think your conference is a bit broader scoped than just power electronics. So what we refer to in the talk is a power converter. Here an example is shown, but independent of the specific application, for example, conversion of a DC type of input to an AC type of output, or any other type of power conversion. All these systems share a very similar structural and design features. So they are based on a switching cell, which is basically built with semiconductor devices. Then some thermal management assembly, some thermal management system, heatsink fans, cooling pumps, and then typically input and output filter in the form of magnetic components and capacitors. So, and we typically assess the performance, the characteristics of these systems by means of three main figures of merit. The most important one is probably efficiency, that is a measure of the excess energy that we need to circulate to carry out the function. Then power density is also extremely important, and recently in particular with the proliferation of electric transport, the gravimetric power density, that is the weight for a given power rating, is becoming extremely important. And the last one is reliability. When we try to map these figures of merit, these requirements onto the semiconductor switches, which are at the heart of the system, basically what we would want or what we would need to have is an ideal switch. So a switch that does not dissipate any power either in the on state, in the off state, or during the commutations. Okay. In reality, we do not have ideal switches, and the situation today is that we are very good at manufacturing devices which are optimized either for very high switching frequency, but then at relatively low power handling capability, for example, for the case of drift-based devices of MOSFETs. And we are equally good at making devices that are excellent for on-state conduction, so large bipolar type devices like thyristors with very large power handling capability, but then limited in the maximum switching frequency. Okay, switching frequency is very important for reducing the sizes mainly of the equipment. So this is the situation today with silicon devices. What has happened very recently is that a new class of devices, since about 10 years ago, has become a commercial reality. They are called wide bandgap semiconductor devices, and they promise to give us the possibility to cover this range of operation where we can have both the high power and the high switching frequency capability. So they really stimulated a lot of research, and I wanted to show you a little bit of the learning we have done so far in the last 7 to 10 years and what is happening from now on. So I have these 4 sections in the presentation. I will start try and explain why wide bandgap semiconductors are better than silicon in power conversion, and then discuss what are the shortcomings of the solutions that we have developed for silicon in making the most in exploiting the full potential of wide bandgap technologies, and then present what is regarded now as advanced options, advanced solution, then leave you with just a few conclusions. Okay. So when we design a semiconductor power device, and we try to approximate the ideal switch that I mentioned earlier, we typically have to enter some trade-offs between the optimization for on-state, off-state, and switching. For the on-state, the most generic type of equation you can use is the one reported here. And what I just want to maybe highlight in here is that as engineers, as design manufacturers, the parameters we can influence is, for example, the doping levels, these N and P symbols that you find in these equations. And we would want to make them as high as possible so that we can have very high current density with very low voltage drop, that is with contained power dissipation. Diffusion currents help us to achieve high current density with low voltage drop, but they imply a penalty on the switching performance because they imply some charge storage and charge extraction phenomena. Okay. When we look at the off state, on the other hand, the equation we refer to for the voltage rating of the device is as indicated here, where the critical value of the electric field is usually a constant of the material we are looking at. So again, the engineering parameter in this equation is the doping level N, and it is clear that it intervenes in the opposite direction to influence the blocking state as the on state. So if I make N very high, I can improve on state performance, but immediately I have a penalty on the maximum voltage which I can achieve. And you know, it is interesting to scale devices up in voltage in power electronics, because for a given power rating, if we increase the voltage, we can decrease the currents. And today, still most of the losses are ohmic in nature. That is, they depend with the square value of the current. So there is a great interest in going towards higher and higher voltage ratings. Then in relation to the thickness is embedded in this equation in the gradient of the potential. And again, we would want as thin as possible devices to get very good on-state performance. But for the blocking capability, we need to accommodate a depletion region, which again is inversely proportional to the square root of the doping we introduce for a given voltage level. Okay, so again, a limitation to the minimum thickness we can achieve coming from the trade-off between these two operational states. Then to optimize switching, again, we would want thin dies with low diffusion components, which goes against both the blocking capability and partly the on-state performance optimization. So why does wide bandgap revolutionize this approach, these trade-offs that we need to enter? So I want to report a single parameter, a single value, which alone is enough to justify a lot of what is going on or the expectations associated with wide bandgap devices. And it is the value of the critical electric field of the material. So here, for example, in going from silicon to silicon carbide, we get about a factor 7 higher value of the critical electric field. Okay, if I go back to my simplified equations here, a factor 7 higher critical value of the field means that I can dope a factor 49 higher without any detriment of the blocking voltage capability and improving the on-state performance a factor 50 in one step. Okay, so that is a kind of a little revolution which is reshaping, which is changing the way we approach the design of power semiconductor devices. So what has happened with silicon is that, with the transition to silicon carbide, for example, which is today the most mature wide bandgap technology, has been that we started to design MOSFETs, which in silicon are limited, let's say, to about a few hundred volts, can be designed in silicon carbide with very good characteristics up to 3.3, 4.5 kilovolts. Okay. We can keep thicknesses of the substrates much smaller because we can dope much higher. And basically, even when we design bipolar type of devices, we do not see the need for high diffusion current components, so that the switching is also extremely fast and very efficient. Okay. This is not the only property. There are also other properties, in particular, the value of intrinsic carrier concentration, the larger bandgap, the higher thermal conductivity, which are also contributing not only to make the devices more efficient and, let's say, more power capable for a given switching frequency, but also capable to operate at higher temperatures, which gives us the possibility, together with the higher switching frequency capability, to increase the power density and the reliability further. Okay, so these devices were expected for a long time. Some key technological breakthroughs were achieved only around 2010, 2011, and since that moment, let's say, people have really started to invest or to consider this technology. The number of manufacturers has increased very rapidly, and today we observe the creation of a supply chain which is sufficiently diversified to make this technology a commercial reality. So what has happened at the beginning? Like with all new technologies, it has been tried out as a so-called drop-in replacement of silicon in established technologies. So we also took that approach. That was the first bit of research we did. And what you see here is an inverter rated for 2.5 kilowatts, so for residential applications, which was actually a commercial product. So it was a result of a collaboration with a company. This was for photovoltaic applications. And we tried it out. The commercial product existed in silicon, and it was designed around the nominal switching frequency of 16 kilohertz. Okay. So we experimented by changing the silicon devices to silicon carbide and gallium nitride, and we demonstrated that we could easily push the switching frequency up a factor 10, which is really a very large step change, with a very moderate penalty on the efficiency. Okay. In this case, we are looking at a renewable energy application, so efficiency is extremely important. But if you consider a more general situation, for example, that of electric vehicles, in some cases, if you can demonstrate a reduction of the size and the weight, that favors the overall system efficiency even if the power converter's efficiency is reduced of 1 or 2 points percentage. Okay, so the drop you see here in the efficiency is absolutely something that in many applications could be considered because you have benefits in other parts of the system. So what does this possibility imply? What does it entail? It means that we can reduce the filter size and weight. So the starting point here, the filter at 16 kilohertz weighed about 1 kilogram. Okay, and we achieved a reduction in both volume and weight of about a factor 3, but let's say with the requirement to increase the switching frequency a factor 8. Okay, and here you see that the test was done actually under exactly the same operational conditions for the inductor, both in terms of RMS current and current ripple, which determines the losses in the core and the temperature of the inductor. Okay. Other advantages that could be drawn and could be demonstrated are in the reduction of the heatsink, because we could operate this at higher temperatures than 50 degrees heatsink, again without any significant penalty at the heatsink level. Okay, so these results were of course received very well. Many people, many groups have produced results which indicated that the efficiency could be stepped up, that the power density could be increased, but there is a general understanding that they are probably not enough to justify the higher cost of the technology. So right now the approach has changed slightly, or it is starting to change, and rather than just drop in, replace silicon with wide bandgap technologies, bespoke solutions for wide bandgap devices are being developed. Okay, so I would like to review now the shortcomings to making the most of wide bandgap technologies with conventional solutions. For this, please allow me to refer to a standard two-level inverter with a motor, because it is the most widespread applications for power electronics. It is considered to make up about 90% of all power electronics application. So this is an extremely successful topology because it is very simple, it has low components count, it gets the job done, and it has been, let's say, deployed universally. Okay. In reality, many applications, however, and in particular when you want to start to use wide bandgap semiconductors, you are usually not in a position to use the inverter connected straight to the machine, but typically need to introduce some filter elements because of the very high EMI signature of the fast switching devices. On top of that, again, in particularly in relation to the development of electric transport, there has been a growing need for stepping up the voltages. You know, this topology is only step down, it cannot boost. So there has been an increasing need for introducing also a boost stage on the input side so that we could work with higher voltages and reduce the size of the machine, operate at higher rotational speeds. Okay. So when we go from the initial idea to the final solution, it stops being so simple. It does contain quite a large number of devices. It contains a DC link capacitor, which in many applications is a bit too bulky and reliability critical. So there are many shortcomings to still going on with this approach and fully exploit the capabilities of wide bandgap devices. Specifically, some of those issues are when we go from silicon to silicon carbide, we can increase without doing any particular design optimization the switching speed a factor 10. Okay, so we can reach this has been demonstrated in a number of papers from university laboratories. You can very easily reach 50 kilovolt microsecond DVDT, whereas today machines, insulation, cables are typically rated for only up to 5 kilovolt microsecond. So you typically have to slow down the devices, and then you lose the benefits that the technology could give you. On top of that, that implies issues with reflection, noise, electromagnetic noise in cables if the cables are relatively long. We have issues with integrity of the machine bearings, of the insulation of the wires, of even the semiconductor devices or passive components. And we can typically increase the switching frequency in real applications about a factor 4, not really the 10 I have shown you earlier. That can be done in a laboratory setting, but when it comes to a real application, it is very challenging to really go for that step change in the switching frequency. So, and this is as far as the topology, so the circuit operation is concerned. On top of that, we also have to consider the technology, that is the way we are used to packaging, to assembling the semiconductor devices and then mounting them into the system. So where we are coming from is a type of power module, multi-chip power module, as indicated here, which corresponds to a single IGBT or a single transistor with its anti-parallel diode from a system design point of view, even if internally it contains up to 24 IGBTs in parallel. More recently, this approach has been changed to the integration within one module of half-bridge legs, which makes more sense from a current commutation point of view. It can help you reduce parasitic inductance, voltage overshoots. So it does bring some benefit in the switching of the devices, but it is for sure not yet the best solution, the ideal for making the most of silicon carbide or gallium nitride devices. On top of the performance issues I just mentioned, we also have a number of issues associated with reliability. Devices we usually look at as if they were all uniform in their operation. In reality, a semiconductor device is made up of a very large number of cells, which inevitably include some spread in their main parameters of design. On top of that, to implement a power module, we parallel multiple devices, and we have within the assembly a number of interface layers so that we always deal with the presence of weak spots inside the power module. Okay, so we are actually operating the single chip very often outside of its safe operating area without realizing that. So the issues, because of the feedback loop, the positive feedback loops that exist between the power dissipation and the temperature in a typical power electronics application, the outcome, the results of, let's say, the progressive stress applied either by thermal non-homogeneities or electromagnetic non-homogeneities are either failures of a subset of devices within the chip or progressive degradation of the constituent materials, solder layers, wire bonds, which lead to loss of reliability. When we use these packages developed for silicon with silicon carbide, we achieve very poor reliability results. There is a lot of unsatisfaction about the reliability of silicon carbide modules built with the solutions developed with silicon. Okay. So what is happening now? What are we looking at? One of the most interesting things that is happening, I think, is a return to some concepts that had been proposed really very long ago, but that were really not interesting with devices switching at low frequencies. Whereas now with devices that can switch at very high frequencies, there is a return to these topologies of sinusoidally modulated inverters. I report here the one that is at the moment probably receiving most attention, which is the Y inverter. Okay, this is an inverter. I present here the single cell schematic, and to explain its operation, basically, this is like a non-inverting buck boost converter. And if you simply modulate rather than with a constant value, you use a duty cycle which follows a sinusoidal waveform, then you can produce at the output of each phase a sinusoidal voltage waveform with integrated boosting capability. So the advantages of this solution as compared with the traditional one of the boost DC converter plus inverter is, first of all, that we eliminate the DC link capacitor. We still have output capacitors, but these are all very small value. They can be implemented with film capacitors. You do not need the big bulky capacitor that is typically implemented with electrolytics, and you get much higher reliability, much better performance. On top of that, one of the main interesting aspects is that you inject, onto the load, or you produce on the output, basically a single spectral component that is that of the fundamental. You see in these simulation results, we see a little bit at the switching frequency, but compared to a traditional modulated inverter, this is absolutely negligible. Okay. In these results, I want to show that although the voltage you see that you get out of each single phase is offset, so it is clearly only higher than zero, only positive, because I can only either step down or step up the input voltage, but I cannot reverse the sign. When you apply this to a three-phase system, you have a cancellation of the offset in each of the phases. And so from the point of view of the three-phase load, there is absolutely no difference, and this solution can be applied very successfully with high machine motors. Okay. We have worked in particular at an advanced implementation which uses interleaved design that gave us the possibility to reduce to contain the volume of the magnetic components. And we are getting, here you see some representative waveforms, we are getting very good results, in particular by applying non-continuous modulation schemes, which is, let's say, a kind of modulation approach which goes really hand in hand with these solutions, which require really very high switching frequency. Another advantage that you have from this solution is that you see on the input side, because now your input and output switches are decoupled from the inductor, whereas in the case of the boost plus inverter, they share the same DC link voltage. This gives you the possibility to use for the input side low voltage devices rated in relation to the battery voltage, whereas you will still need high voltage devices with a rating equal to 2 times the peak voltage on the machine, but they will be switching not against a square wave, not against a constant DC voltage, but against a sinusoidally varying voltage. So by definition, a voltage waveform which has a much smaller average value and thus much lower switching energy. That is what enables you to increase the switching frequency significantly and really make the most of wide bandgap technologies as compared to the traditional solution. Okay. On top of that, because it is based on these essential cells that have been developed for DC-DC converters, it is very easy to also implement, accordingly depending on the needs of the application, this inverter solution either as a boost-only cell or an interleaved parallel series cell to boost up the current capability or the voltage capability. Okay, so definitely this is something that is very interesting as far as topologies are concerned. What is going on in the field of technology? There is a move to new type of packages in which no bond wires are used anymore. Rather, the switches are sandwiched between substrates, and they can dissipate much more power. Power heat can be extracted by both the top and the bottom of the devices, and they tend to be cooled within polymeric type of frameworks, which act at the same time as the package and the cooler. Okay, so they help us reduce significantly the number of interface layers, improve the power density and the reliability of the assembly. These approaches have been brought to quite an advanced level with silicon. Here I show you some work we had done with building vias in the ceramics with some advanced interconnect features still on a silicon inverter for automotive. Here you see another example where we had introduced modularity for the case of a matrix converter used in avionic applications. What is happening now is the transfer to wide bandgap, to silicon carbide, in which in particular it is important to have this kind of very high frequency compatible terminals, very small parasitic inductance to enable very fast switching without high voltage overshoots, and a trade-off with the cooling because of the higher temperature capability of the devices. Okay, this has been demonstrated now at relatively low voltage, 1200 volt class. It still needs to be brought up to 3.5 kilovolt and more. Okay. So in conclusion, so there is a clear understanding today that square wave modulated voltage source inverters will not really give us the possibility to exploit the full capabilities of wide bandgap devices. The trend today is towards a higher voltage, higher speed, higher number of poles machines, which require quite a high voltage. And if we work with boost or higher battery levels, systems become very complicated. So two solutions in particular, the Y inverter and the current source inverter, which I did not mention here, are receiving a lot of attention. They enable really much higher switching frequencies, very high efficiency, very high power density, and excellent electromagnetic signature, which are all much, let's say, making it a lot easier to meet these requirements coming from the application for progress on the machine side too. Okay. Also, what is happening today is that we are starting to look at power converters, so topologies and technologies in a joint way. Whereas traditionally they were looked as two completely separate things, there is today an understanding that if we really want to make some major progress forward, we really need to develop bespoke technologies for applications. So that is changing a lot the way we integrate semiconductors. Okay. So this is the message I wanted to leave you with. I hope we have time for some questions. Thank you very much for your attention.
Thank you very much, Professor Alberto. I think we a little bit tight on time, but still have maybe time for one or two questions. Is there any question from the audience? Or can leave in the chat box. Okay, then I may ask you some thought on which approach should power electronics engineer or researcher adopt between going directly to use wide bandgap device or considering using some alternative topologies as you present.
So the topologies I presented are best suited for wide bandgap. So you will not get very good results if you use these topologies with silicon. There have been a few attempts in the past, but they were very poor. You really need very high switching frequency capability. Then at the same time, a transition to wide bandgap in a conventional topology will probably not give you all the results that you might expect. You will find that there will be many limitations to exploiting the devices fully. So the best way forward is to join the two things, is to understand the characteristics of the devices in depth, and then develop solutions which can exploit these characteristics. That is what is giving the best results.
Thank you for the clarification. I think that's about the time for the session. Thank you again, Alberto.
Thank you very much.
In giving our speech, please give him a big hand for this. Thank you. Hope that you can join us in present next year.
I hope so too. Thank you very much. Have a good conference.
Thank you. And that concludes our session in the afternoon. So we may have a little bit time to change to other session. So see you in maybe 5 minutes. Thank you.